The biggest difference between just measuring with GNSS and monitoring with GNSS is that when we're monitoring, we're always measuring kind of in a dynamic environment. So up until now, we've been looking at kind of static measuring. And what that really means is that we're taking one measurement and treating it as a snapshot of what's happening. And so we can kind of treat that as a more static environment. So on any given day, we went out and measured all these pieces, and they are in these locations, and we expect them to stay still. When we're monitoring, even when we're measuring the same points and we expect them to not be moving, because we're measuring the same points over time, we're measuring them today, tomorrow, the next day, the next day, the next day. Everything is going to be changing. It doesn't matter if your structure is moving or if it's not moving, because we're measuring over time. We have changes in the satellites that we're tracking, the weather, the orbits of the satellites, all these different things, the temperature, all these different influences that can influence the measurement, the error correction, the movement of the structure. So no matter what we're doing, we're always assuming that when we're monitoring, it's a dynamic environment, and we have to kind of take that into account. What that looks like in more of a practical application. So we have a region of influence. If you guys attended our last webinar, you kind of remember what this is, but I'll cover it again. So the zone or region of influence is an area that may be moving and is being influenced by other factors, or it's a region that is moving and has potential to influence some other outside areas. So an example of a region that may be moving and is being influenced by local factors is something like a railway or a building that's been stable for the last 50 years. It's been built, it's been around for a long time. All of a sudden, you're introducing some sort of outside influence. So whether you're doing some excavation nearby or some boring or construction next to the building or the railway, you kind of expect that this has some sort of influence on the structure they're measuring because it's within a certain region, right? So there's potential to influence that structure. A really common application is that railway application where we have a railway sitting, and then all of a sudden you have to do some excavation within 50 or 20 feet of the railway. So you expect that could influence the dirt and the structure that's holding that railway up. So you have to monitor to make sure that it's not being influenced by that construction. An example of a region that is already moving is something like a sinkhole or a landslide. And what we want to do is be able to measure that landslide or earth movement as it's moving. But we also want to be able to measure the surrounding area to see what is being influenced. So maybe we have a sinkhole in a neighborhood, and the sinkhole is only 50 feet across, but it has potential to influence an area 100 feet around it. We want to make sure that we're measuring that sinkhole and also measuring those surrounding buildings to make sure that everything is safe. Visually, what that looks like is we have a setup here. So this is an example of like construction in an urban environment. So we have our region of influence, which is just the area that the construction is in that we expect it to be able to influence some sort of movement. So in this example, we have two buildings that we're monitoring. The construction is nearby. And so we have our GNSS system set up on the buildings to measure that offset or any potential change in the location due to that construction. And then we have our base stations set up outside of the zone of influence. In this case, the thresholds for the movement, so what we're looking for and what we actually expect to happen and what we hope doesn't happen are going to be determined by a few different things. One is going to be the natural behavior of the structure. So again, the building is going to move as much as they're going to move on their own. So it's important to set up your instrumentation before that construction starts and understand how those buildings move without outside influence. That way, when the construction starts, you can understand what movements are normal and abnormal. You also want to determine the thresholds before you start, so that way you can determine the best instruments to use. In some cases, using something like a single base station setup and some basic GNSS receivers is okay because you're not looking for super high precision. But if you need really high precision, you're going to want to think about multiple base stations, those network corrections, high precision antennas, faster tracking receivers, all these different kinds of things. You also want to make sure you set up your baselines as early as possible. Baselines are those measurements we have before all that outside influence starts. And again, it just helps you understand that natural movement. If you just measure for one day, it might not be enough information to say, look at the daily variation in the structure. But if you set it for a week or 2 weeks or 3 weeks or a couple of months, it's going to really let you understand how everything behaves on the site. So that way, when there is an outside influence, you can understand if the influence is actually moving the buildings or if things are behaving normally. It just gives you a whole lot more information. The second region of influence is one that's already moving. This is really typical in like landslide or regional settlement or seismic monitoring, where the things are already moving. And so we want to kind of set these up reactively and understand if things are stable. So if we're looking at a fault line that's moving or a landslide that's moving, they tend to move very slowly over some period of time and then accelerate and move a lot at once. So we want to understand, again, that natural kind of stable movement. And then we also want to understand when things are accelerating and kind of have an understanding of how it changes. The biggest difference here is that this is a reactive setup. And so it's not always possible to determine your baselines and thresholds ahead of time. So what you want to do is set up and measure for a little while and understand how things behave as they do normally. And then you're going to be reporting on things like velocities instead of on just raw displacements or coordinates, because you kind of expect things to be moving in that dynamic environment. But again, the same basic principles. So we have some sort of thing that we're monitoring in that region of influence. And then we have our base station set up outside of it. That way, when there's any movement, we can hold it fixed to these base stations to understand how things move relative to some fixed point. Perfect. With that, I'll kind of get into a comparison and contrast of total station versus GNSS. So again, this is part 2 of our 3-part series on monitoring principles and best practices for all the different methods. The previous webinar covered total station monitoring. If you need more information on total stations, you can go back and watch that recording. I won't get into it in too much detail. But the basic principles that we're looking at. So total stations use or can measure in very high precision. So when we think about GNSS, we think about centimeter, and in best case scenario, sub-centimeter. When we're thinking about total station, we're really thinking about millimeter and sometimes sub-millimeter accuracies. Total station can also measure a lot of targets from a single location. So it's really good at measuring a smaller area with a much denser coverage of prisms and target locations. Whereas GNSS is a single discrete point measuring one location. So it's not going to be able to measure 100 targets from one location, but it's going to be able to measure one discrete point and cover a much wider area. So total stations are limited by line of sight. They're an optical instrument. They use a laser to track and record positions, where GNSS uses those base stations to record stable positions and error models. And then you can set up a bunch of antennas covering a much wider area. So total station is good for covering maybe 1,000 meters. GNSS is good for covering anywhere from, a much tighter location covering a few kilometers all the way up to hundreds of kilometers or covering entire cities and states. So GNSS is really good for that wide area measurement. Total stations can also only collect data on the minute or hour kind of measurement interval. So they go and they measure discrete points, run around, collect that information, process it, and display it all at once. And you kind of set that interval. So you want to set it usually to be as quick as possible, but it does take a few minutes or up to a couple hours to run. Where GNSS can get that really high frequency measurement, so measuring in the 20 hertz range or the sub-second range, and transmitting that data in real time. So you can have near instantaneous reporting and alarming based on that GNSS position. Another advantage to GNSS is that you can have kind of multiple processing methods. So you can do that real-time processing with that high-frequency data collection and get instantaneous alerts. Or you can do post-processed methods and collect data over an hour or 12 hours or 24 hours at a time, average that all together and process it and get a really high precision position out of your processing. That really lets you go down from like centimeter level to that sub-centimeter level. But again, it takes some more time. So you can use both processing methods on the same project, get those real-time kind of worst-case scenario alerts, and that high-precision long-term trending, really useful for things like seismic and landslide and everything like that, where we're looking at both long-term slow movement and worst-case scenario rapid, quick, large movements. Some common applications for GNSS. Really, the most simple application is just measuring the location consistently over time. There's a lot of places that we can do it. When we talk about monitoring, there are a few that really stand out. So one is landslides and seismic and regional settlements. So these kind of all group into the same concept, where we have some sort of wide area that is moving. Again, this can be moving rapidly or it can be moving slowly. When we think about especially seismic drift, we can think about something like a fault line that's going to be moving at most maybe a centimeter per year. But then in the worst case scenario, in an earthquake situation, it's going to be moving maybe a meter at a time over a couple of minutes or a couple of seconds. And so it's really advantageous to combine that long-term post-processed high precision tracking and movement data where you can measure the change every day. And the change every day might be as small as a millimeter. And then you can add in that rapid alerting. So if there is a seismic event, which are typically unpredictable and they happen at random times and there's really no way to accurately predict it, you can measure it and then alert based off of it. So if there's all of a sudden a movement on the fault or the movement is accelerating, you can send out kind of that early warning to the area surrounding it and make sure that people know what's coming and know the situation. Same idea for landslides and regional settlement, where landslides are just the same idea, but in a much smaller area. So you can accurately measure and alert based on slow and rapid movements. Same with regional settlement. So when you think about regional settlement, it can be something like a big sinkhole or above an underground mine or something like that, where we're really looking at a much more widespread area that is settling outside of what you would expect. Dams are another common application, especially when we talk about large tailings dams or concrete structures. where we need that rapid alerting. So we expect that the dam really doesn't move at all until it moves quite a bit. And so we really like to see that, again, combination of long-term post-processing high precision with that rapid alerting. Dams tend to also be very high risk, and so it's really important to alert the second that some movement happens. So having that real-time processing and that 20 hertz tracking can be extremely important. Another application, and it's a little bit more specialty, is called integrated survey. So if anybody attended the last presentation on total stations, you remember that the whole thing is based off of having reliable and accurate backsites. The backsites stay out of the zone of influence and they're expected to be stable. Same idea with the base stations here in the GNSS processing. And actually, if you want to learn more about how the base station location is treated as fixed and the monitoring locations are treated as floating and kind of do that least squares adjustment, you can go back and watch the previous webinar. It's the same math and the same adjustment process. It's just a different method to collect. But going back to the integrated survey, so with the integrated survey, what we have is the idea is that we can set up a total station with everything inside that zone of influence, even the backsites. But because the GNSS is much better at doing wide area monitoring, we can have our base stations far away from the zone of influence, 20 kilometers away. So even though the total station can't see outside that zone of influence to reliable backsites, it can get corrections from the GNSS antennas. We can co-locate optical backsites with monitoring antennas for GNSS. And then we have updated locations of those monitoring prisms. So every time we run that resection, even though those antennas and prisms are moving, we're getting new locations for them. So we can more accurately and reliably run that resection and get a realistic representation of what's happening with our prisms based off of that GNSS correction.